So with us today is Roman Binkert from the Technical University of Munich, and he's a PhD candidate and researcher at the Embedded Systems and IoT professorship. And he's basically looking at cyber physical IoT systems and is leveraging the Web of Things and to basically integrate different information sources and devices to the industrial metaverse. And of course, the part that relates to today's presentation is a central goal of his work, and it's to basically ensure that complex system data is made intuitively understandable and actionable for both autonomous agents and human users. With this, I will give it to Roman.
I'll start. Thank you for introducing me, Ege. And yeah, like Ege already mentioned, today I will be presenting an approach I developed to integrate or allow multi-agent systems to interoperable communicating with cyber-physical devices and also other agents based on the Web of Things. This is based on a paper we published last year. So if you are interested even to read further after today and the discussion afterwards, you can also visit that and read there. I also prepared a small slide to introduce myself, but Ege already did this, so I'll skip this for now. So basically the motivation we had for this approach is that, for example, in this use case, a manufacturing cell, we might have a robotics arm that is actually interested in moving an object as soon as it's somewhere and then processing it to bring it somewhere else. But to know if there is actually an object present, it needs to ask or needs to communicate with a sensor to know if there is an object present. And as you might know, if you're familiar with the Web of Things and maybe also with other manufacturing applications, this can involve quite a bit of a hassle to actually just get this data, because you can have a lot of different protocols that you might need to deal with, different endpoints and so on. I will get into details about that a bit later, but this is already where the Web of Things and especially the thing description is already quite helpful, because it describes easily how you can interact with a device and what kind of information you can get from that device. So basically, once we have this already, the robot arm can get the information from the sensor, and therefore can basically have this simple agentic. We will also get into this, how this works a bit later, but this agentic goal basically to, if there is a sensor, the object detected by the sensor, I want to take that object and process it. And then we might have more than just one object, and we want to be a bit faster, so we might want to introduce another robot arm. And again, this robot arm also needs to contact the sensor, and it needs to make sure at once if there is a sensor detected by the object, it wants to grip the object and then move it. And maybe this object is at the same starting point or the same pickup point, so therefore maybe the robot arms also need to communicate with each other to make sure that they not clash into each other or ask the other one if it's currently moving or not, and to ensure safety there. And you might have noticed already that this robot arm on the left side is basically using moving, and the other one is using the word carrying. And then again, robot arm A is using take, and the other one is using grip. So they use kind of the same or similar words for describing the same manipulation, but it's not the same word. So just by programming, or if we just have these agents themselves, they wouldn't be able to understand what the other robot is doing. And this is basically what we wanted to help solving with this approach. And our idea was to also use the Web of Things and the thing descriptions to solve this. And I will now explain how we do this in a few steps. Basically, let me sum up again what the problem is. So we have multi-agent systems, and they are good for autonomy and self-organization, and they can provide a goal-oriented programming and communication, but they are not that good at providing interoperability. And this is where the Web of Things comes into play, because it provides uniform parallel capabilities of things and also protocol agnostic communication. So our idea is here to, again, like I said, use the thing description to describe what the agent is capable of, and to also basically map the internal naming an agent is using to bigger semantics with an ontology. And therefore, to allow each agent to reason on its own by using its own naming, its own word. So, for example, it can ask for state or something, and then based on the thing description, our approach can map this to actually tell the other agent what this agent actually wants to know and translate this basically. For example, from grabbing to taking and so on. And this is our idea. And since we now have people from Web of Things community group and also the agents community group, I want to briefly introduce both concepts, and I hope I don't bore you with it, but I'll try to introduce those briefly. So basically the Web of Things, the central part that we now use is the thing description. The Web of Things itself is an aggregation of standards, but the thing description is one part of it. And it is used for a standardized description of how you can interact with a device. It allows you to describe the interaction affordances, data schemas, and also some other additional stuff like security configurations or protocol bindings. Let me give you an example here of what the Web of Things basically tries to do. So here we have a smart toaster, we have a temperature sensor and a smart light bulb. And basically, if we reach a certain temperature in the toaster, we know our toast is ready, and then we want to turn on the light bulb. And therefore, we want to basically get the current temperature from the temperature sensor and then turn on the light bulb. Sounds easy, but actually can be not so easy if you really try to do this. Because, for example, in this case, the temperature sensor might be using Modbus as protocol, and the LAMP might be using HTTP. And then to actually get the actual temperature data from the temperature sensor, you have to perform a lot of steps, like finding the API description, then finding the concrete request, and then also finding request parameters like the endpoint, the scaling, the endian. And then you get some data, but then you still need to be able to interpret the data. So you get a number, for example, but then you need to know if it's Celsius or if it's Fahrenheit and so on. And the same happens, or similar thing happens if you want to turn on the light bulb. You also need to go through all this information, and this already leads to a lot of code that you need to write and a lot of things that you need to understand. And with the Web of Things and the thing description, this will get a lot easier, because instead of having all this complex step, you just basically scan a QR code or somehow link to the thing description of that device. In there, you see in a standardized format what this device is capable of, what it provides to us. For example, the temperature sensor provides us a temperature in the unit Celsius, and we get a number, not an object or something, but just a number as response. And then all the protocol stuff is in the forms part. And the Web of Things therefore allows us with the protocol bindings to directly send a request without knowing how Modbus in detail works. And therefore, we can just say we want to read the property temperature, and then we get a temperature value. Similar, it works for the light bulb. We can easily find the correct interaction, the correct request we need to send, and we can find the value that we need to send to the light bulb to then invoke the action, set color with the input 60 to turn it to yellow, for example. This is the idea, and for that, we have 3 different interaction affordance classes: properties, action, and events. Property basically describes a property of a device. So you can, as a consumer, read the property and then you get a response. So for example, in this case, from a ventilator, you can read the current rotation speed, and then it will return you a number. And this is how a property is described. Basically, you can read this. Sometimes you can also write it. Or you can also observe it to be notified when it changes. Another thing is action. So if you want that thing to start doing something, then we send the request, the thing starts doing it, and it might also send a response back. Can be synchronous or asynchronous, and this can also be described, but this is basically an action. And finally, we have the interaction. The last interaction for this class is the event. This is something more asynchronous. So first we start to subscribe to the event, then nothing happens. And if then on the thing itself something happens, then we get notified. So for example, if the thing itself is overheating. Again, like I mentioned, we have a thing description that can look somehow like this. And this is basically describing in a standardized form in a JSON file how to interact with this device. And you can also add more information to that. You can enrich the thing description by linking, for example, to ontologies, like for example, in this case, to the serif ontology. And therefore we can say that this property is actually serif property, so we can gain a more common understanding of what this property actually means, or what this turn on command actually means. And we can then link to the ontology and actually read through it and get more information what it means. So much about the Web of Things background, basically, of what we need for this. Let me now also briefly introduce agent system and how agents in this for this work are working and what you need to understand there. Agents in general are a big word at the moment, I guess. A lot of people are using it, but let me try to break it down what which kind of agents we used in this work. So basically, an agent or agentic programming is a different kind of programming, I would say, because you don't have this classical if-else statements and like first asking what is the current state, and then you get some value, and then based on that you have an if-else or while loop or something, but you have a more agentic or more high-level way of programming devices, and this results in a more autonomous device that can also be more proactive and reactive. Basically, what we do is we program the agent with some desires and some plans to reach that desires. And basically, as you can see on the right side, this is an agent reasoning cycle. So we start on the top left here. We have some input from a sensor, and these then are perceptions. So what the agent basically has its input values, and then we have some beliefs that the agent, these perceptions lead into beliefs that the agent thinks what is the current state of its environment. Based on these beliefs, then the agent compares these beliefs to its desires that we have programmed to the agent, or that it can gain some other ways. We will talk about this in a bit. But then it can have some desires. This is basically what it wants to reach. And it compares if its belief about the environment is different to its desires. And if this is the case, it tries to see if it can somehow change it to change the environment more towards its desires. And then it has an intention to change it, basically. And then it goes through its plan library, a collection of functions, basically, on how to change the environment and through some effectors. How you program this can be, for example, with the agent programming language JSON, as you can see here. And there you program a plan. In this case, it would be once we get the desire to process some green object in this case, then we first print that we are now actually processing print to just inform us as a human, basically. And then this leads to 3 sub-desires. First, we want to move to a certain position, then we want to drop the object, and then we want to go home. And this is basically, again, other plans on how to reach that desire. I hope this makes it clear already, or clear enough. We will also get later into a bit more details. I hope then it gets even clearer. But this is basically how an agent system if with this belief, desire, intention architecture works and reasons. And then if we have a multi-agent system, we don't only have one agent, but we have multi-agents. And then we can also don't have just sensors and effectors, but input and output can also be communication from and to other agents, or as we will show, also to other devices, not agents themselves. And for this communication between different agents, there are so-called performatives, and they are basically describing what the agent wants to achieve with this. So either for example, we can have tell, ask, achieve, and ask how. Tell is just to share a belief. Ask is basically read or get information about something, asking another agent if it knows something. Achieve is to ask the other agent to try to achieve a goal, to delegate a goal. And finally, something maybe a bit different to what we know from general programming is to ask how. So we can also ask another agent if it has an idea on how to reach a certain goal that I have, but I don't know how to solve myself. And then again, based on all these background information, we can formulate again our approach to, again, create interoperable cyber-physical multi-agent systems with Web of Things by doing these 3 steps. We first want to match or map agent speak to Web of Things interaction affordances, and therefore allow agents to use the Web of Things as communication layer and also easily interact with any kind of Web of Things described device. We also describe the agent's capabilities itself with a thing description, and first to allow other agents to know what this agent is capable of, and then lastly to also match the internal naming of an agent to an ontology, to a common ontology, to then use this common ontology to translate different internal namings between different agents to another agent. For the mapping, we basically propose this mapping schema. So basically, if an agent wants to ask something from another agent, this will result in reading a property, observing a property, or subscribing to the event. And then this, if the other side, the other thing is also an agent, this will lead into adding a test goal to the other agent. So then it knows I want to find out if this exists or if this is this case or not. Or if it's just a conventional thing, it will just read the property and then whatever you have programmed in the background there. Similar also for the achieve. This will just maps easily to invoking an action and then adding an achieve goal to the other agent's belief base, or then the other agent has the intention to achieve this goal. A bit different, doesn't map as perfectly is the tell performative, because in this case, either we know we can map it to the right property, then again, we add a belief according to that property to the other agent. But if there is no according property in the other agent's thing description, it's hard to map. And then we propose maybe just use a tell action as fallback. And then add this to the belief base. Finally, the ask how is is another action we propose to add to any agent's thing description to then see if the other agent has a plan to knows how to achieve this goal. Like this, we can already enable agents to interact on a Web of Things base layer, basically. And therefore, we can also get all the benefits from Web of Things regarding the protocol agnostic communication. But we also, since using the thing description, are able to use this semantic or introduce a semantic translation, like I mentioned already. And this, again, I want to briefly show here. So the agent internally has this plan, like on the right side. It wants to move to a position, it wants to drop an object, or it wants to, and then it wants to go home. this is its internal naming. Like this, it's not translatable to any other agent or any other device, basically. And then we use the thing description, like here, to add the annotation to any ontology that we want to have, basically. So for example, here we can translate that our internal naming go home from our agent maps to the go home action of this ontology. And then again, we can, in the other agent, also map another similar named action also to the go home ontology action, and therefore then translate between this internal namings. And like this, we can also translate not just single action or a single belief communication, but we can also translate even more complex plans, at least if they exist, or if they only have plan steps, so parts of the plan that are mapped through the thing description to the straddle ontology, and then they can also be mapped to the other agent. Let me show you this and evaluate this maybe with some examples. First, in this case, we just demonstrate that we have some agents that are now also able to communicate with devices. So the robot arm itself is an agent. It asks the conveyor belt agent if there is a sensor, if there is an object in front of the sensor. Once there is something, then it knows, okay, now I have to go to pick it up. And then the other agent is also moving it to the other conveyor belt. I have another example where maybe it gets a bit more clear. Again, here we have two agents that want to communicate with each other and that also want to exchange plans. So we have agent A and agent B, and the goal of these agents is to move objects that are arriving here to the dedicated belt. So in this case, we have a red cube, and this needs to go to the red belt, but the agents themselves don't know this. So only this agent knows what to do with blue cubes and what to do with green cubes, and this agent only knows what to do with red cubes. And therefore, the agent on the left side doesn't know what to do with red cubes. Then it looks, for example, something like this. So again, here we have the left-hand agent. It knows that once an object is detected, then I want to first pick up the object, and then I want to process the object. But I only I have depicted only that it knows how to move an object of color blue. And now we have a red object, so it doesn't know how to move this. And it should ask the other agent if it has a plan. And this other agent actually has a plan to move a red object. But as you can see here, it uses different naming conventions. So first the move at, then the release, and then the homing, instead of move to, drop object, and go home. And then we basically use the thing description as I described to map the internal namings and then to translate the plan such that the other agent gets a new plan in its own internal naming and is able to process also the red cube. Finally, I have also a video of this. Basically, here again, we have the left agent not being able to move the red object. Only knows how to process a green object or a green cube. It picks it up. Now the right-hand robot doesn't know how to process a blue cube. We allow it to ask now. We wait a bit, we allow it to ask the other agent how to process this object. It will then ask it, and as I have shown previously, translate the plan from agent A to agent B internal naming, and then it's able to manipulate this object. yeah, so much about our idea of how to use the Web of Things, and especially the thing description, to allow agents to translate between different concrete or internal namings based on ontologies, while still allowing them to using their internal naming schema. Yeah, thank you for your attention.